Hi there, this is Joshua Meyer with Group 8. Our group chose the table tennis scoreboard for our final project. The requirements of this project were that there would be two teams, each with scores that could be incremented, decremented, or cleared, which would be displayed on two 2-digit 7-segment displays. A winner would be displayed if a team reached at least 11 points and surpassed the other team by at least 2 points. We also added that if a team reached the limit of our score counter, they would be declared as winner. This would avoid the score counter resetting to 0, possibly causing the opposing team to be declared as winner. Now, there are 3 main segments to this circuit. The first is the actual score counter that displays the points of each team. The second is the logic circuit that defines who wins each match and when they win. The third wasn't required, but we decided it would make sense to add it, which was the win counter. This counts and displays how many matches each team has won, and pauses score inputs when a team has won, so that once a winner's been declared, this cannot be undone by a new score. This segment would allow also for players to play a best of 3 match, for instance. These 3 segments really form the main building blocks of our circuit.
Hi, I'm Griffin Johnson, and I'm going to be explaining to you the first stage of the table tennis scoreboard. So we have our user inputs here, up, down, for each player, along with the clear. We went with an LPM counter to keep track of the score for either player. And we did the LPM counters simply because they're easily configurable and give us all the functionality we need to properly keep track of the score and give an increment, which is up, a decrement, which is down, and a clear. We have an asynchronous clear, so whenever the users want to restart or adjust the score, they can clear at any time. This up-down feature allows the counter to either count up or down, and in order for the counter to count up, up, down must be true, and we only want that to happen when we press up and only up. So that is why up has a AND gate here, along with down being false. So the only way up, down is true is if only the up button is pressed, and in the same breath, the only way that up, down is false is if down is pressed. If we want a decrement, we press that, and up, down will become false. Both the up and down inputs are ordered together and plugged directly into the clock. We did it this way because we wanted to avoid, for instance, if I held down the up button and had it set up in a different manner with a separate input while the clock was running, this would allow the score to keep incrementing as long as we held down the button. We thought that would be more of a nuisance for this type of scoreboard, and so we figured as long as we press the button, no matter how long we held it down, that will only go up or down once, and we figured that would be more useful in this scenario. So that's why we decided to plug them in directly into the clock. And you can see the output of both counters go to instead of a BCD to 7-segment decoder and then a 7-segment display. Obviously, we're not able to build this in real life, and we're only doing simulations here in Quartus, so we felt it would be more useful to just have a group output pin here, and that would, we were able to change these bits into actual decimal numbers in the waveform simulation, and that way it'll be easier for us to interpret and see what's going on when we're checking the functionality of the circuit. So obviously in real life, we would have this hooked up to a driver, hooked up to a 7-segment. However, we chose to do something a little bit different, so it's easier for us in this situation. Now last, we have these tri-state buffers that I did not mention yet. The reason we have these buffers is we also wanted to avoid erroneous wins being dealt to either team. And so there's a situation that we thought of where, let's say, Team X wins, and then for some reason, Team Y increments a couple of times, and all of a sudden they're assigned a win when the game is already over. We wanted to eliminate that possibility. So we took whenever X or Y winning is true, we hook those up to an OR gate, and then it gets inverted. So every time a team wins, the up and down features are disabled. And the only way to start a new game is for the users to hit clear, and that will clear both scoreboards simultaneously, reducing any chance of an erroneous win being dealt to either team. So that's the reason for the buffers, and those are connected all to the same one for both the Team X and Team Y. So that's the first stage of our table tennis scoreboard. Now Ben will give you an explanation of the rest of the logic.
Hello, my name is Ben Lumens, and I am also a member of Team 8 for our Logic and Digital Design Final Project. Griffin previously showed you the first part of our logic diagram. That showed the logic for counting Team X and Team Y's score. Now I will show you part 2 and 3 of our logic diagram. Part 2 shows the logic to determine a winner from the counting. And part 3 counts up the number of wins for Team X and Team Y. Here I will show you parts 2 and 3. This is part 2 of our logic diagram. As you can see, there are 2 outputs, Team X wins and Team Y wins. These outputs are determined by 2 different conditions. One condition has 3 steps and one condition has 2 steps. Let's start with the first condition. The first condition takes the count of Team X and Team Y's score. It is determined by first subtracting Team X from Team Y or Team Y from Team X's score, and determining if a team is winning by at least 2 points. That is the first part of an AND gate, 3-input AND gate. Next, it determines if a team has at least 11 points. This is how normal ping pong works. If you reach 11 points and beat a team by 2 points, you win the game. The third condition just determines if a team is winning. This is how the AND gate works. Next, it connects to a 2-input OR gate, the output of the AND gate does. But also, we have another condition for the 2-input OR gate. That condition determines if a team has at least 31 points. We're using a 5-bit counter, so the maximum number of points a team can reach is 31 points. So if a team hits 31 points, then they are the winner. Let us go to part 3 of the logic diagram. Here's part 3, the final part of the logic diagram. As you can see, we ended with Team X wins and Team Y wins. Here, it takes that output and adds a counter to determine how many wins a team has. And this counter will determine up to 3 wins, as we have a 2-bit counter. Also, we have different inputs for the counter so that a team can increment or clear their score how they want, as they may have previous games and want to continue those games. This is how our complete logic diagram works.
Hi, this is Daniel Anderson from group project number 8. We had previously gone over a little bit of the functionality of the entire circuit for our table tennis project here, and what I'll be doing is going over some of the simulations and showing the functionality, the proper functionality of the counter, as well as the implementation of the project, in which it calculates a winner after 31 points due to the bit limitations in the project. As we can see here, this is showing the clear function, which clears all these scores in the counters for the beginning of our circuit there. We have Team X's count up function. We have Team X's count down, Team Y's count up, Team Y's count down. And then we have the values of Team X and Team Y here. So if we look at our counter for Team X counting up, you can see that at each rising clock edge, it counts 1 up from each one here. And for the purposes of this simulation, we are using a decimal value as the output instead of the 7-segment display. Typically in a real life situation, we would have the counter connected to a 7-segment driver as well as a 7-segment display. But again, for the purposes of this presentation, we are using decimal radix here to show you the simulation. So then we have the countdown increment here, so we can see that on this clock edge, that's counting from 6 to 5, and then as that goes up, counting to 4. Then when we get the clear all here, we see that both values have cleared. We can also see that the value of Y counts up at the same exact time on the rising edge of each clock there. And then decrements for each Y count down, and then they both clear. And then here you can see that they can count at different increments, different speeds for the two of them. The counters are triggered by the input of the clock, so the actual input is the clock, therefore eliminating any issue with holding down the button and then having the counter just continually count up if you were to hold the button too long. So that's how we fix that issue. Now I'd like to take a look at the implementation of the 31 point score maximum here. Counting up, we see that both teams are tied, counting equally, and therefore there is no winner due to the fact that you have to win by 2. And then we do see that once Team X reaches 31 points, they do win. And then we also see here that the win counters here count how many wins that team has. And then we also gave the functionality to include a increment win for Team X and increment win for Team Y in case you needed to fix the amount of wins that a team has. And then you have the clear all wins function. So this win counter would keep a tab of how many wins each team has as well.
All right, my name is Zach Sargent. Today I'm going to be showing you the output of our ping pong scoreboard that my team and I have designed, and then I'm going to be showing you that all of our functions function as they function appropriately. All right, so as you can see with this picture here, this picture is describing the overall, I guess, functionality of the circuit as a whole. It's all those past 2 pictures kind of put together in one. So what this is showing is the basic scoring of table tennis and of our logic circuit. So in table tennis, if a player reaches 11 and there's at least a 2-point margin, they automatically get the win. And also, if there's a point difference of 2, then they get the win with that as well. Then in our circuit too, we designed it where if one player reaches 31, then that player gets a win. So You can see this here in the counter where player X has achieved a value of 11. And there's at least a 2-point margin between player X and player Y. So therefore it deems player X the winner of that round. So then the clear button is pressed. Both scores go back to 0. And the game is resumed and incremented respectively. So here you can see players are neck and neck essentially up to this point here where player Y has a score of 24 that increments to 25 and then to 26, while player X stays at a score of 24. So then this difference here of 2 points, the 26th and 24, registers as a win for player Y. So as you can see with the 11 that player X achieved, that registered as a win out of the best of 3 for X. So that was 1 win on X's part. And then 26 out of 24, where player Y is the winner, at that instance, X still has 1 win, and then Y is incremented. The best of 3 for output for player Y is incremented to 1. And that is basically the overall functionality of our circuit.